So the last thing I want to talk about is gases. So I'm going to make this kind of a second video because it's a totally separate topic. So part 2 of today, we've talked about liquids and aqueous chemistry. We've talked about solids and how they can precipitate out of solutions. So today we're going to talk about gases. There can be gas phase reactions for sure, but we're just going to focus on gases that aren't reacting. So you might have seen the ideal gas law at some point in high school, but I think it's really important to focus on the ideal part of this. So the ideal gas law doesn't always apply. We assume that the molecules are really small relative to the empty space between them, and also that they don't interact. And so if I shrink my space down really small so that the molecules are really close together and kind of big relative to how much white space there is, or if I have two different kinds of molecules that really want to interact, then the ideal gas law stops working. So it's important to realize that the ideal gas law isn't perfect all the time. So if you start seeing like the pressure is super, super, super high, maybe set off some alarm bells about, is this gas ideal? That said, most of the time when we're at normal pressures that we're working with day to day, and most gases, the ideal gas law gets you pretty close. It does a pretty good job. So the ideal gas law is PV equals nRT. This one I probably would memorize. I use it so often that I don't need to think about it anymore. I remembered it as PivNert is the way that I first remembered it. So PV equals nRT means that the pressure in units of atmospheres. So at sort of sea level on Earth, the pressure is 1 atmosphere times the volume in liters equals the number of moles of gas times this constant R that I'll get to in a second, times the temperature in units of Kelvin. So R is a constant. So in the units that I've used here, it's 0.08206. You don't need to memorize that. That would be given to you. But there's also tables of it in all sorts of other units. So if you had your pressure in some other units, you can either convert it to atmospheres, or you can just use a different ideal gas constant. And so you might remember when we were talking about units, in order for PV to equal nRT, these units need to cancel out. So with my R, I have my liters times ATM on this side. They cancel out on this side. And my Kelvin and my moles on the bottom so that they cancel out with the moles and temperature on top. So pressure times volume equals moles times this constant R that we always know times temperature. And one important thing is that these units of temperature are in units of Kelvin. So if you have your temperature in Celsius, we never really use Fahrenheit for just about anything. So if we have our temperature in Celsius, we just have to add 273 to get our temperature from Celsius to Kelvin. And so what this means is that if I know the volume, the number of moles, and the temperature, I automatically can just calculate what the pressure of my gas is. So if I know all of these things except one, I can always just calculate the fifth one using the ideal gas law. Does anyone have any questions on how to use the ideal gas law? Okay. So once you know the ideal gas law, you can get all sorts of other relationships from it. So if I have a liter of gas at a pressure of 1 atmosphere, and I don't change the temperature or the amount of gas, but I increase the volume, I can try to figure out the new pressure. So how do I do that? I'm starting at this initial state. So I'm just using subscripts by my pressure, volume, etc., to indicate that it's at my starting state, so state 1. So at the beginning, in state 1, my pressure is 1 atmosphere. I have 1 liter of gas. My temperature is 300 Kelvin. And I haven't calculated my N1, but I could. I could use the ideal gas law and calculate N1. I just haven't done it yet. It wasn't given in the problem, but I could do it using the ideal gas law. I would just plug in P, V, and T, and I know R all the time. It's just a constant, and I could solve for N. In my second, that's the ideal gas law. So I'm just putting these subscripts that in state 1, P1 times V1 equals N1 times R times T1. In my second state, I don't know my pressure. That's what I want to solve for. My volume, I told you I've changed my volume to 2 liters. I told you I didn't change the temperature. So my temperature is still 300 Kelvin. And my number of moles hasn't changed either. So N2 equals N1. So I can plug those numbers into the ideal gas law too. And so P2 times V2 equals N2 times R times T2. So N2 is N1 because that didn't change. And T2 is T1 because that didn't change either. So if I'm just substituting in N1 for N2 and T1 for T2 because they didn't change, then I can also say that P2 V2 equals N1 R T1. Does anyone have questions on what I did so far? I'm just plugging in the variables that I know into my ideal gas law.
You just keep it the same because they were the same in state 1.
Yep. So whatever didn't change, I know that N2 equals N1 and T2 equals T1. So I just switched N1 and I changed N2 to N1 and T2 to T1.
Okay.
Because they're the same. So now I know that P1 V1 equals N1 R T1, but P2 V2 also equals N1 R T1. And so because P1 V1 equals the same thing as P2 V2 equals, then I can just set those equal to each other. So P1 V1 equals P2 V2. Does this make sense? So there are all these gas rules. So this one is called Boyle's law. And I think sometime in high school, I had to memorize all of these, like Boyle's law, Dalton's law, all this stuff. But really, once you know the ideal gas law, laws like this just come straight from that. So I hate memorizing stuff. So I would not memorize that P1 V1 equals P2 V2. I would just know that if you start from the ideal gas law, whatever things don't change, you can lump together and set everything else equal. So in this case, I know P1 and V1, and I know V2, and I want to solve for P2. So I'm just going to plug in 1 atmosphere is my initial pressure, 1 liter is my initial volume. My final volume is 2 liters. So my final pressure must be 0.5 atmospheres. So I could have taken my state 1, solved for the number of moles. I know that that doesn't change. So I can go over to state 2, and now I have V, T, and N. So I could have solved for the pressure, but this just sort of removes a step. So if I know that the number of moles and the temperature doesn't change, I can just skip those steps and set them equal to each other. So the point here isn't Boyle's law is P1 V1 equals P2 V2. The point is that once you know the ideal gas law, you don't have to memorize any other gas stuff because you can get it all from the ideal gas law. So I'm going to have you try to come up with a similar thing. So with everything else held constant, what's the relationship between pressure and temperature? So now pressure and temperature are changing, but volume and number of moles are not. I'm going to give you about 5 minutes in your breakout room. So I'll pull you back at like 11:55 or 56, and then we'll go over it. And if you're watching this later, pause to practice. Okay, welcome back. So all we have to do is follow the same sort of process that we had before. So in state 1, we know that P1 V1 equals N1 R T1. That's always true. PV equals nRT, and the ones just mean I'm in my starting state. In my second state, I know that P2 V2 equals N2 R T2. So that's just PV equals nRT, but in our final state. So I'm changing pressure and temperature, but I'm keeping everything else constant. So I'm keeping R, the volume, and the number of moles constant. So V1 equals V2, N1 equals N2, and R is always just a constant. So I can substitute in V1 for V2 and N1 for N2. So I have P2 times V1 equals N1 times R times T2. And then I can lump all the things that I know together with the things together. And on the other side, I can lump the things I don't know. So pressure and temperature are changing. So I lump those together. So I'm dividing both sides by temperature, and then I'm dividing both sides by volume. So on this side, it's maybe a little easier to see. So I have pressure and temperature. Those are the things with the 2's. Those are the things that aren't the same in state 2 and state 1. So I get those on the same side by dividing by temperature. And then I get all the things with 1's on the same side by dividing by volume. So N1 times R divided by V1 is the same in both state 1 and state 2. So I can say that P1 divided by T1 is the same as P2 divided by T2. So I never need to memorize this relationship between pressure and temperature for an ideal gas, because I can just figure it out starting from the ideal gas law. Does anyone have any questions on how I did this? What I want to emphasize here is that you don't need to memorize stuff. Every once in a while you'll need to, but often if you just have a few tools like PV equals nRT, you can move them around to figure out a bunch of different relationships. Any questions? Okay, so that's it. That's it for all of our chemistry content. As I've mentioned, tomorrow we're going to have panelists that will be past GSIs from Chem 1A. So come prepared with questions for them. They'll have really useful advice for you about how to succeed in chemistry and how to study for exams and common questions or problems that they see people have. So I think it'll be really useful for you guys to get to meet them. But also you can ask anything about, why did they decide to go to grad school? So if you have any questions you've thought of in advance, you can submit them here. But I hope you'll come tomorrow ready to discuss with them and learn something and ask questions. So I stuck the form in the chat one more time. And yeah, that's it for the chemistry content. Stay after if you have any questions. And obviously I'll be there tomorrow as well.